Dr. Jeremy Davis previously worked for the United States Army Corps of Engineers Engineer Research and Development Center with research focus in computer vision applications on embedded systems. He also previously worked for Babel Street, Inc., where his research was focused on applying natural language processing techniques to open source intelligence mediums. Currently, he works as a principal research engineer at the Center of Cybersecurity Research and Education at the University of Alabama, Huntsville, where his research is focused on applying machine learning techniques to bolster cybersecurity applications. Dr. Davis received his PhD in 2022 from Mississippi State University. His research focus is primarily on deep learning in the cybersecurity, computer vision, and natural language processing domains. His research interests include using AI to enhance cybersecurity applications, object detection in image and videos, AI on embedded systems, bridging the gaps between visual and textual signals, scene understanding, applying AI to OSINT signals, adversarial AI, generative AI, and retrieval augmented generation. Welcome, Dr. Jeremy Davis, to the stage.
Hey, good afternoon, everyone. Thanks for that introduction, Joseph. I appreciate it. So I will try to keep this as short as possible so we can get to cocktail hour early. I know everybody in here would appreciate that probably. There we go. So yeah, I'm Jeremy. I work for UAH, the Center for Cybersecurity Research and Education. And today I just kind of wanted to talk about what AI is and kind of a history of AI through the years. We'll go through the genesis of the research. Then we'll talk about computer vision, natural language processing, and the timeline of that. And then a little bit about where we're headed and where we might be going. So what is AI? So these days, AI is really an umbrella term. You can think of it like it's just a broad general term like engineering. There are multiple sub-disciplines of engineering. There are multiple sub-disciplines of artificial intelligence. So you can do a quick Google search and you'll come up with 100 images of different representations of what AI actually is. So I actually just Googled fields of AI, and it gives you the following diagram. So the first one here, it separates everything, natural language processing, machine learning, speech, all these different fields here. When, you go to the next one that you pull up, and it's a different diagram where it's kind of it's a similar separation, but it's a little bit different. One thing that I'd like to point out is machine learning is actually used in all of these now. So we'll talk a bit about that in just a few minutes here. So this diagram is pretty cool. It separates it out a little bit better. So you have, natural language processing, computer vision, robotics, knowledge representation and reasoning, and neural networks and deep learning. So machine learning actually encompasses neural networks and deep learning, and that bubble there even says that above it. So this diagram I found really interesting because it has types of AI. So artificial superintelligence actually concentrates on AI that's evolved past us. So AI that can think better than us, that can do everything better than us. Luckily, we aren't there yet. Who knows if we'll get there? I don't have that answer. Artificial general intelligence is AI that is able to self-teach itself, kind of like we are. We start learning something, we want to dig more into the field, we want to learn more about a particular topic. Artificial general intelligence can actually do that. That's kind of where we're working towards right now, but I don't think we're completely there yet. And we'll talk a bit about that in a bit too. So right now we're still kind of in the ANI domain, which is artificial narrow intelligence. And that just describes AI that can perform a set of tasks and do that set of tasks very well. Okay, this final graph here is, I think this encompasses the field that we're in right now, or the state of the field right now very well, because most everything that we talk about these days is all machine learning. So deep learning, reinforcement learning, supervised learning, unsupervised learning, it's all a form of machine learning these days. We'll go into some of the different topics and some of the different algorithms there here later in the presentation. But it's important to note that machine learning actually extends out to all the different subdomains like speech, text, vision, audio, all these different domains. Okay, so how many in here have used at least one of these or all of these? Everybody, right? Pretty much. Okay, so everybody's used deep learning then. Uh, if you've ever used Snapchat to put a filter on your face, you've used a computer vision model. That's deep learning. If you ever use messages to auto predict your text, you've used a prediction, next word prediction. That's deep learning. Instagram, tag your photos automatically. It's all deep learning. Self-driving cars with Tesla, deep learning. ChatGPT, obviously, that's all generative AI. What's called generative AI these days. Then you have your other computer vision models like DALL-E, all your generative models. So you give it a prompt and it'll actually come back with a image that you want. So all of those are a form of deep learning. So most everybody in here has used deep learning. Okay, so now we'll go a little bit down the rabbit hole. So what I want to talk about next is how do we get here? So we'll explore that rabbit hole now. Before we go too far into that, I just want to go a little bit into my background. And I'm sorry, you guys, forgive me for flipping the pages up here. I'm used to having speaker notes, so I didn't have a monitor here, so I'm going old school with paper. So this is academic Jeremy. So academic Jeremy, I got my master's degree in 2011. My master's degree was focused mainly on heuristic search, which was a subfield of artificial intelligence as well. And like Joseph just said a minute ago, I got my PhD in 2022, and that focuses on computer vision and scene understanding. And then there's professional Jeremy. And professional Jeremy worked at the United States Army Corps of Engineers Engineer Research and Development Center, where I worked on path planning, so I got to use my heuristic search a little bit. I worked on some computer vision stuff with object detection. We were putting embedded systems on drones and doing some stuff with thermal and LiDAR and various other things, so that was pretty cool. And then I worked for Babel Street from 2017 until 2023, where I did a lot of natural language processing on open source intelligence. So we trained a lot of transformers, a lot of your large language models to do some open source threat intelligence there. And most recently, I began working at UAH, and we're trying to combine the worlds of cybersecurity and artificial intelligence together. Because what we want to do is we want to make these models where they can kind of bolster the cybersecurity processes that we have today. And that's not me, that's Midjourney. I wish I was that dapper. He looks a lot more comfortable in that picture than I look right now. So I wish I looked that good in a suit. But yeah, heuristic search, what is that? I thought you said deep learning. So heuristic search was a prominent subfield in the 2000s. That was, back in my day, that was what everybody was using. So chess, checkers. Does anybody remember Deep Blue? Chess machine, that was heuristic search. It was a modified minimax search, which is just a heuristic search, adversarial search. So deep learning actually wasn't widely available until 2014, and that was with Caffe. And I would find it hard to believe that there are still people that are using Caffe now. Maybe they are, but it's in legacy systems, so everything switched over to TensorFlow and PyTorch around 2015, 2016. Caffe actually really doesn't exist anymore. I don't think you can find anything that will compile that. In the stone age of deep learning, when I first started working with it, you had to compile TensorFlow on a HPC, and what you did was you compiled it from source with CMake, and you just crossed your fingers that you didn't segfault the whole thing and get yourself fired. But now you could all pull out your laptops and run deep learning models on there with no problem, and that's just been within the last 8 years. Some of my takeaways from the last 15 years here is I miss heuristic search. I really enjoyed it. It makes sense. It's easy to follow. So if you guys want to go down the nostalgia rabbit hole, just read some stuff about heuristic search. I don't even know if most professors still teach that anymore in intro to AI classes. So a lot of AI research is actually geared towards playing games. And the reason that is like games are a well-structured environment. Games have a well-established set of rules. Games have a well-defined objective function. So if you can teach your AIs to play chess, tic-tac-toe, checkers, and all this other stuff, you can evaluate its progress and evaluate its accuracy and effectiveness. I also watched a rapid evolution of the field in just the last 15 years. So when I first started, like I said, heuristic search was all the hot craze. Then we kind of switched over to feature engineering, which feature engineering is a little niche task there where everybody was going through manually crafting features, and we'll talk a bit more about that later. And then we switched from feature engineering actually over to deep learning. So where feature engineering, you were manually creating your features with models. Deep learning actually learns the features for you, and that's why deep learning is so successful and has been. Okay, so why did I go into AI? All right, any 80s and 90s kids in here besides me? All right, great. Everybody knows who this is, right? Okay, so I probably watched this movie when I was 7. I'm sorry, Mom, it's totally kid inappropriate. But I was just blown away about the idea of having a cyborg that could learn and that could, would follow me and would do whatever I wanted it to do. just that whole idea. And of course, Terminator 1, that wasn't like that. We'll get there next. So Terminator 2 is when he became a good guy, right? So in Terminator 2, I was a teenager when this came out, and this just resonated with me because what if I had a T-800 follow me around all the time? Something that I could teach, something that would be my best friend, all this stuff. I know it sounds sad, I didn't have a bad childhood or anything. I'm just saying, that would be awesome to have, right? So at that point, I knew I wanted to work in AI. As Sarah wrote to John, the future is not set. There's no fate but what we make for ourselves. Okay, so for those of you that are a little bit younger than I am, we used to have to go to these things called libraries to look up stuff. And I'm from small town Mississippi. There was not very much interest, if any interest at all, in computer science, much less artificial intelligence in small town Mississippi in the 1990s. So my whole future had to be put on hold because I didn't know where to get started, and I actually didn't get back to working in AI until I actually went to college for computer science. And that's a whole other story. That's pretty funny, so I'll leave that one for the Q&A session if you guys want to hear it. All right, so enough about me. So we'll go ahead and get started. We'll start at the genesis, if you'll indulge me there. So this is Alan Turing. Alan Turing is arguably the most influential person in computing history. He worked on everything. Alan Turing came up with cryptography as a discipline. He actually invented artificial intelligence as a discipline, although he called it machine intelligence. So in an unpublished report from 1948 called Intelligent Machinery, Turing actually formulated the whole field of heuristic search, where heuristic search is basically you have objectives and you actually assign weights to choices you make. If you look at it like a graph or a tree structure for any computer scientist in the room, you weight your nodes of your graph to say, okay, this one's going to give me a more likely or more probable or more acceptable reward. So he also formulated the idea of training a network of neurons to simulate how the brain operates, and that's actually the first postulation of a neural network that in recorded history anyway. So he actually proposed the Turing test in 1950, which is still something that's huge to this day. So the whole idea of the Turing test is very simple. If there's 3 people, you have one interrogator, so one person's asking questions, and you have 2 other entities in another room that the person asking questions cannot see. The goal of the interrogator is to determine which one is the human and which one is the machine. So if the machine can effectively fool the interrogator, it's considered to be intelligent. And to this day, nothing has passed the Turing test yet. It's arguable that ChatGPT can, but ChatGPT will give you some very forward and upfront disclaimers when you ask it risky advice, like medical advice. It will tell you, I'm a LLM and I shouldn't be trusted. So that on principle disqualifies it, but it's still arguable. Okay, that's the wrong John McCarthy, I'm sorry. Okay, the real John McCarthy that we're talking about today is John McCarthy actually founded artificial intelligence as an academic discipline, and that was at a Dartmouth workshop in 1956. This is widely considered the birth of artificial intelligence as a field. He actually coined the term artificial intelligence because Turing was calling it machine intelligence. He also developed Lisp, which is a programming language called Lisp processor. And what Lisp did was it allowed you to formulate programs in artificial intelligence languages. Like it was just made specifically to write AI programs. And that was widely used up until the 80s. I think it was like the mid-80s when Lisp kind of fell out of favor. He also helped establish SAIL, the Stanford AI Lab, and there's a lot of cool stuff over the years that have come out of the Stanford AI Lab. And next we have Mr. Rosenblatt. Mr. Rosenblatt introduced the idea of the perceptron. So the perceptron was funded by the Office of Naval Research, and it's the first documented idea of a neural network, the first documented proposal of a neural network. Turing proposed it in intelligent machinery. This is the first implementation of one. So the perceptron probably ran on a computer the size of this room. It was a 5-ton computer, and the only thing that it could do was if it was fed a series of punch cards, it would tell you if the punch cards were punched on the right or punched on the left. So back in the 50s and 60s, before personal computers were a thing and digital computers were a thing. You actually had to write your programs in punch cards. So all this perceptron would do would, okay, this one's punched on the right, this one's punched on the left. And Mr. Rosenblatt is quoted as saying, this is the first machine capable of demonstrating an original thought. And that's after he demoed the perceptron. Another interesting thing too, so you imagine this is a 3-layer network. These things were, in today's world, they're small, they're minuscule. You've probably got 20 of them running on your phone right now. I'd be willing to bet that every app that you're opening is running something that's more stringent computationally-wise than a perceptron. But it took a room this size to run the first neural network. And this is actually the first neural network. So this is a diagram of the perceptron. And I don't know if you guys can read that. X is your input, so your inputs come in, they get averaged together through weights, they go through a summation function, and then they go through an activation function, and you get an output. Simple format, but all of the current state-of-the-art models that we're using today, including ChatGPT, including DALL-E, they're all based on this simple idea. And this is the perceptron just formulated as another way. Does anyone recognize that equation, what it might be? Does anybody know the equation y equals mx plus b? That's slope-intercept form of a line, right? At its heart, that's all the state-of-the-art models are doing. There's some stuff on top. There's some nice sprinkled sugar on top. At its heart, all machine learning models are trying to do is draw a line in space to make data separable. The trick is you have to figure out a way to take your data that you may not be able, with your eyes, to see is separable and project it up into a dimension where you can draw a hyperplane where the data is separable. That's a lot of math talk. I won't go into that because I promised my boss I wouldn't. But just know at its heart, it's simply trying to draw a line. It's trying to draw a line to separate one class or multiple classes from each other. Pardon me with my old school paper here. Yeah, these early networks, they had to be ran on configurable hardware. That means that every time they wanted to train a network, they had to re-implement the hardware. They had to readjust it. They had to remake it. Okay, so digital computers weren't around for, I think, 15 to 20 years when Rosenblatt proposed this perceptron. So they limited these things to 3 layers because nobody wanted to configure more than 3 layers for a configurable hardware machine. And these things took weeks or months to train. So in the 50s and 60s, AI research there was so much excitement around it. Government agencies were funding it. Universities were funding it. They believed that there'd be fully sentient beings in 20 years, fully intelligent machines in less than 20 years. And there was just a general sense of excitement. However, in the 1970s, we had the first AI winner. So what ended up happening is researchers were posing this problem as, we're going to make a machine that could do everything. So we're going to make one machine to rule them all, Lord of the Rings style, right? So what they ended up doing was they overestimated the capability of the hardware and the software that they were trying to write. So when they failed to realize the difficulty of the problems, when all these contracts came to you that had been funded and the results were just subpar or non-existent, the funding just got cut almost overnight. So the funding disappeared, and a lot of this was because of limited computing power. So as we talked about, you had to have a 5-ton computer to run some of this stuff. Like how many of those could you really feasibly have? So limited computing power, a failure to understand the actual complexities of the problems they were trying to solve caused this first AI winner. However, in the 70s and 80s, the late 70s and early 80s, there was a revival of AI research. So optimism around the field returned. And there's a few people here that are responsible for this. The first one is Ed Feigenbaum. And I know the earlier presentations, we talked a little bit about expert systems too. All expert systems do is they demonstrate that an AI can solve one task really well. So an expert system, it's just a set of rules. It's an if-then rule base. You can think of it like a fuzzy logic system. That's a form of expert system. So expert systems were the first type of AI machines that were capable of getting good results on one specific task. And that actually revitalized the interest in the field and revitalized the research. And then we have John Hopfield. Now, John Hopfield is probably the most responsible for revitalizing the field of neural network research to get us to where we're at today. And Hopfield networks were a specific type of one-layer neural network, but what they did was they showed that neural networks, given a strict domain or a limited domain, they could solve or converge to the same problem space within the same constraints. They would converge the same problem space every time. Before it was believed that neural networks would just evolve chaotically, so the weights, you couldn't update them, you couldn't train them, the weights would just do what they're going to do, and you had a black box, and you just put data in, you got data out, and you just hoped it was right. Hopfield proved that it was mathematically possible to prove that these networks would converge given a limited set of constraints. David Rumelhart was one of the first people to really do neural network research, but he didn't even know he was doing it at the time. So he actually proposed backpropagation, and then him and Jeff Hinton and Ronald Williams came up with the idea of applying backpropagation to a neural network. Backpropagation just means taking reverse differentiation. So what backpropagation allows you to do is when you run your data through your networks, you can train it, you can pass the error corrections back through the network. So you're taking the gradient and you're passing it back through the network. Okay, so backpropagation is still used today. It's still the most widely used training algorithm today for train all of these state-of-the-art models that everybody's using now. But unfortunately, in the late 80s and early 1990s, we had another AI winner. So you remember me talking about the Lisp machines? So these Lisp machines fell out of favor because you had very specific machines, and well, now digital computers are available to the public. Nobody wants to buy a Lisp machine. So now you have all this useless hardware laying around. They're expensive to maintain. They're very difficult to update. These personal computers could do what a Lisp machine could do and more, so nobody was buying those. So funding was cut significantly because everything was developed on the premise of Lisp machines. And Lisp did kind of evolve and become more of a programming language instead of a programming machine, so that's why it was still used through the mid-90s. But even with the breakthroughs with the neural network training and the ideas of backpropagation and the Hopfield nets, the hardware still wasn't there, and you still could not keep up with the software needs. So let's try this again. Okay, so in the mid-90s, we had another a research of enthusiasm again for AI. So we had increased computing power. We had AI research that was modeling specific problems, and it was able to solve them efficiently. And around this time, AI kind of split into all those different fields that we saw in the first few slides here. So before we go into the split, and specifically I'm going to talk about computer vision, natural language processing, and multimodal models, just because that's my research area. You have to give a shout out to the godfathers of deep learning. These guys are all still active in the field today. So you have Yoshua Bengio, Jeffrey Hinton, and Jan LeCun. These three guys are credited with inventing deep learning. So all of your models that you're using today, we all owe to these three guys for the most part. So you know, that's Jan and Jeffrey's X or Twitter or whatever the cool kids are calling it these days. That's their handles, and Joshua has his own blog that you can read. And they still all do a lot of research, and they all have some pretty interesting thoughts on the field. And just to clarify, this is in no way an exhaustive list of all of the contributors to the field. There's too many to name. I just wanted to kind of highlight some of them that everybody may or may not have heard of. So yeah, we'll start with computer vision. So computer vision was actually born, for lack of a better term, in 1966, and that was an MIT summer project. So a professor tasked his graduate students with implementing foreground and background segmentation. And what I mean by that is, imagine you have a car on a road driving around. So you want to look at everything but the car as your background. And you want to look at the car as your foreground. So if your car is driving at you, the car should be in the foreground. Everything else behind it should be in the background. That project was a massive failure. They did not realize how hard that was, because it's still a challenge today for some of these models to do that. But it did give the field traction, and it was considered the birth of computer vision. So in the late 60s, a Japanese researcher, and I will not even try to butcher his name, so I didn't put it up here, proposed the idea of the neocognitron. So that's a self-organizing feature network. So imagine your network configures itself. So you have a network and you pass some input in, it reconfigures itself to do what you want it to do. It had limited It had limited success, but it's the first use of convolutional layers. So in 1989, Jan LeCun, who we just saw, proposed the Linnet 5. And Linnet 5 was the biggest breakthrough in vision, and it still kind of is one of the biggest breakthroughs in vision. And what Jan did was he ran backpropagation on a neocognitron-style network. So he stacked a bunch of these convolutional layers, ran backpropagation through it, and it's the first modern convolutional neural network. And what Linnet 5 did was it read handwritten digits. So has anyone ever seen the handwritten digit problem? Okay, that's Linnet 5. Linnet 5 actually created the data set that everyone still uses today as the intro to computer vision. So that's the hello world problem for computer vision, is the handwritten digit recognition. So in the 90s, we had kind of a shift of feature engineering. So whereas neural networks, you just want to pass at your input and you have your weights that we saw like in the perceptron. So those weights are actually your features. So your weights are learned automatically. But the hardware wasn't there. It was very hard to train these things, even up through the 90s. So in the 90s, David Lowe proposed the idea of SIFT, which is scale invariant feature transforms, and that is an algorithm that if you pass through an image or any other kind of text, it will just label a bunch of key points in the image and say, I think these are the most prominent features. Okay, so that's kind of a manual way to generate your features that then you can look at and send through a smaller network. But the problem with these is they're very notoriously rigorous. They're very strict. They're very rigid. You can't tune them very well. So just some of the examples of stuff that used feature engineering was Viola Jones, and that was actually the first face detection algorithm, and that actually was on some Kodak cameras back in the 90s too for face detection. And there was a deformable parts model as well. So what the deformable parts model did was if it would find a person in an image in any configuration. So if I'm up here making a pose, it would still know that I'm a person. Whereas before, it was very hard unless somebody was standing at attention to get a computer vision algorithm to recognize a person. Okay, so in 2006, Pascal Visual Object Classes, or VOC, challenge came out. And what that did was that made a standardized object classification data set. So there's 20 categories in Pascal VOC. It was a yearly challenge they held from 2006 through 2012. And I think a modified deformable parts model won it for the first few years. We're still using these feature engineering models. We haven't really gotten into deep learning yet. So in 2010, the ImageNet Large Scale Visual Recognition Challenge was introduced, and that actually expanded VOC out from 20 categories to 1,000 categories, and that completely eliminated these feature engineering models, because the problem with feature engineering models, you needed to train for all 1,000 of these things. You had to have features for everything. You could not have your network learn these things. But in 2012, Alex, and I will not try to butcher his name, Kraszewski, Jeff Hinton, and Sutskever introduced AlexNet, and that was the first convolutional network that had been applied to any of these data sets. And that was able to get a 16.4% error rate, where all of the feature engineering models in this data set were in the 80s and 90s. So we were able to really greatly reduce the error rates on the using convolutional neural networks. So from 2012 to about 2020, all of the winners of that challenge were formed convolutional neural networks. They're down in the low digits. They're down in like the 1.5s and 2 error rates right now. In 2020, we actually had vision transformers, which is a VIT there. CNNs are still the most predominant computer vision model, but vision transformers are kind of taking over as well. Okay, so for natural language processing has actually been around since the 1950s. So when Turing proposed the Turing test in late 48, maybe around 50, I think it was, I can't remember the exact date, but that actually poses NLP as a research problem. So given 3 entities, how do they communicate? I mean, it's a natural language processing problem. That's what you're trying to get the machines to do. IBM actually created the 701, which was the first translation bot, and it just translated from Russian to English and back from English to Russian. And the bag of words model was introduced. This was kind of a groundbreaking discovery here, and all bag of words was a way to mathematically represent a document, mathematically represent a corpus of text. So, and all bag of words was just the count of the number of occurrences of the word in a document. So, you got a bag of words. So yeah, bag of words is just a simple vector that shows the count of documents, the count of the occurrences of the word in a document. So in the 60s, I know they touched on it a little bit this morning about ELIZA, if anyone remembers that. That was the first chatbot. That chatbot was simulating a conversation with a psychotherapist. I would hate to talk to a psychotherapist chatbot these days. And then in the 70s, everything kind of switched over to these rule-based systems. So Winograd introduced SHR DLU. I'm not sure how to pronounce that acronym, but it was a natural language understanding system. And what it did was it was a simulation that you could just move blocks around. So you could tell it to move the red block on top of the green block, and it would do it. That was really the first natural language understanding system, but it was all based on rules. So in the 80s and 90s, we kind of started forming machine learning or bringing machine learning into the field of natural language processing. So hidden Markov models were used for speech recognition and speech-to-text system. They're also used for automatic transcription. And then there was the term frequency inverse document frequency algorithm. And that built on bag of words, and what that did was that allowed you to represent the meaning or the number of, not only the number of occurrences of a word in a document, but the meaning behind that number of occurrences. And then, of course, your long short-term memory networks for memory. So that allows you to bring in a big, long snippet of text and actually keep track of what you had read before. So from the 2000s to around 2015, we were using RNNs, which are recurrent neural networks, so deep learning, and embeddings was a big breakthrough around this time. And what embeddings does is it builds on both bag of words and TF-IDF, so it's just a better way to represent the input to the network. So some of these embedding models are like GLOVE or Word2Vec, and they just let you capture semantic relationships between the words. They also, around this time, encoder-decoder mechanisms came out, and that was used for translation. Then you had the attention mechanism come out. The attention mechanism was probably the biggest breakthrough because it allowed very easily to represent memory in text. Okay, so from 2017 until the present, Google has done a lot of work towards natural language processing. So they introduced neural machine translation. That was an encoder-decoder model. That's a deep learning model too. They actually introduced the transformers paper. So I know everybody is familiar with ChatGPT. If you're using ChatGPT, it's all based on transformers. It's all based on that paper. All of these large language models today are all based on the concept of a transformer. So in 2018, OpenAI actually introduced GPT-1, and that's generative pre-trained model. The whole purpose of GPT-1 was to do next sentence or next word prediction. So if it saw a bunch of words in a row, what's the probability that the next word would be whatever it chose it to be? So it's just there to generate words. In 2019, BERT was released, and that's bidirectional encoding representations with transformers. So BERT was one of the earliest large language models today. So what BERT's task was a next sentence prediction. So instead of just predicting the word, BERT was tasked to predict the next sentence in the occurrence. So given a paragraph, like what was the likely next sentence? So that's actually the first model that could generate a whole conversation with you. So GPT-2 came out. GPT-2 was similar to GPT-1. They're all the same architecture. They're doing the same thing. They're just trained on more data, and they're a little bit larger. So in the 20s, we're in the age of large language models. So everything we talk about today in terms of ChatGPT and these other models, they're all large language models. Llama, interestingly enough, is the only one that you can download and train yourself for free. You can get that. I know somebody from the talk this morning, they were talking about Hugging Face. But you can go to Hugging Face right now, download Llama and train it if you've got enough GPUs to do it. So the last type of these models are multimodal models, and that's kind of where the shift is going these days. So what a multimodal model is it encompasses two different types of signals, so speech and text, or video and text, or image and text. So the first one of these models was show and tell, and it was a model by Google released with TensorFlow, and it was just an inception convolutional neural network and a long short-term memory recurrent neural network. And what it did was, given an image, if let's say you had a person in a beach, or a person standing on a beach with a kite, this model would send you back the label person standing on beach with kite. So it kind of stalled for about 5 years, but around 2021, OpenAI actually came out with CLIP, which is contrastive language image pre-training, and it was a way to train these models so you can pass it pairs of text and images. So it's kind of building on that idea of show and tell. And then there's Dino, which is self-distillation with no labels. GLIP, which is grounded language image pre-training. These are just some of the recent, most recent breakthroughs. SAM being the biggest one, which is segment anything model. There's already a lot of variants of this. So what SAM does is, you don't have to supply any bounding boxes or any pre-training stuff. SAM just lets you send an image in and it's going to pick out everything, kind of that foreground, background segmentation that we were talking about with the MIT Vision project. It still messes up a little bit, but not too bad. So yeah, that's just short timeline here. So we talked about feature engineering. It's kind of a split through three things here. It's kind of feature engineering, deep learning, and now we're in the generative age. So feature engineering. Okay, so the T800 it had one job. It was an extermination unit. That's all it knew how to do. So the T800 goes to the station, Sarah Connor. He knows she's in there, I'll be back. Okay, well, he doesn't know how to do anything but exterminate, so he thinks he can accomplish his objective by just rolling in and exterminating everybody, and if he gets everybody, so be it. So you can think of these feature engineering models like that. So think about the Viola Jones face detector. Really good at detecting faces, right? What if you showed it a picture of a car? Wouldn't be able to do it. You would get some garbage out. So that was the problem with feature engineering. Unless you specifically trained it to detect certain things, it could not handle new data. Okay, so for deep learning. Okay, here we see John is trying to teach the T800 that he can't just go around killing everyone. And he repeatedly asks why. Well, you just can't. Why? We just can't. So that's kind of how you train these deep learning models. So you pass it in all these different categories. Okay, now I've got 1,000 categories that my model knows about, and it's all just based on how you train it. So you train it with this back propagation style, these back propagation style algorithms, and every time it gets one wrong, that back propagation tells it you're wrong, and it asks why, and it does it until it gets everything correct. So deep learning models still really good at one task, but they extend out to multiple tasks. So here, he's still a really good extermination unit, but he knows the difference between right and wrong now, or good and bad. So the age we're living in now is the generative model era. Now, this is John trying to teach the T800 how to mimic human emotions. Why don't you ever smile? Okay, so Llama, ChatGPT, DALL-E, all these different generative models. They're just outputting what you think you want to hear, or what they think you want to hear. So given a prompt, how can I best represent what this person is asking for? It's not an original thought. Right now, we're not in the state that these machines can come up with an original thought. That's what we're working towards. But with these corpuses, they're still trained, and yes, they're trained, like OpenAI trained ChatGPT on effectively the whole internet. So if it's on the internet, it can come up with something for you. But it's not logically thinking, or logically is not the right word, it's not consciously thinking about the response that it's giving you, and does it answer your question appropriately. Okay, so these generative models are like Arnold here, or the T800. He's smiling because he thinks that's what John wants to see, but is he really smiling? So where are we going? So here, by the end of the movie, the T800 can fully mimic human emotions. Here he's telling John, I know now why you cry, but it's something I can never do. He's showing empathy. He's showing sympathy. He's showing logical, conscious thought. Can these models do that today? I don't think so personally. Can we get there? I don't know the answer to that question, but I think it's really cool to think about. And in a way, it's kind of scary. Will they do our jobs better than us? That's a big fear that everyone has now. I don't think we're there yet. Will we get there? Who knows? Where will we be at in 10 years? Will we still be talking about ChatGPT in 10 years? Or will it be a thing of the past because we've got the bigger and better models that are out here now? Okay, so before I close, I had to work Billy Mays in here. So before I close, just a little bit about what we're doing with AI at the CCRE. So we have a high-speed SCADA simulation. So the problem with SCADA data these days is there's not enough of it to train on. So we have some high-speed simulations to create some SCADA lakes so that people can get our data and train their models. We're doing some automated risk detection. So we're trying to detect and classify malware on protected environments, so SCIFs, different classified environments. And we're going to do that to suggest and deploy some remedies. So we have malicious device detection. And what we're doing there is we're using a hardware approach, embedded systems approach to detect if a chip or board has been altered and if there's a Trojan that exists on a board, on a control system or something like that. We also have our threat counterintelligence that we're working on now. And what that's doing is we're researching and implementing cyber attacks that will target our AI-based defense systems and try to break into them. And if we can break into them successfully, what we want to do is we want to make more robust systems that can't be compromised. And finally, we have our generative AI nullification project that we're just starting up. So we're wanting to research methods. So a lot of talk has gone on about deep fakes here recently. How do you know if something's fake? Now it's so easy to tell. Like, it was so easy to tell that wasn't me. But what if you couldn't? Like, what if you don't know that that's not an original image? There's got to be some signatures in there that you can look for. So, we're working towards giving a really fake signal. How do you work towards, pulling back the original source? So that's all I've got. And I appreciate everyone for listening. So I'll open it up for questions now.
So going back into, or looking back at the 2 winters of AI, do we foresee another winter, lack of computer power? So I guess my question is, do you think there is enough computer power to meet the needs of what we foresee AI bringing?
Sure. So the problem then was everyone was training their own models. Now you don't really train. So you do train, but you're pulling down these already established models, these foundation models. I wouldn't go write ChatGPT or really Llama from scratch. What I would do is I'd pull that down, I'd run it on my data, and I'd set it up to where I wanted it to perform a specific task on my data, but I'd use the pre-trained weights for that model. So you don't have to do like the heavy lifting training, because that even took companies that took OpenAI and Meta. I think OpenAI said it took 6 months or 7 months just to train. We wouldn't have that capability as a person. But now as these models get larger, it's really hard to answer that question. It depends on what's the next breakthrough. And that kind of goes into the, just to elaborate a little bit more, that kind of goes into the transfer learning and fine-tuning domains, where you're not really training anything from scratch anymore. You're just training the model as it is. You're only training the additions that you add to the model.
I'm not sure if you're the person to ask this, but you address the consciousness and AI and some of the fears surrounding AI with us. I'm just wondering, is anyone actively focusing on discernment and consciousness? We have studies at MIT labs and things like that. Is anyone actively focusing on bringing this into AI and training it as part of the equation in the work that you're doing?
Me personally, in the work in what I'm doing, no. I don't think with vision and natural language processing there are. The problem is always to get to that level of consciousness, right now you have to have data, right, to train. And you can still have the whole internet, but it goes back to that generative AI discussion where it might seem like it's thinking, or it might seem like it's talking to you. It's just giving you what you want to know, but it doesn't know if it's. The only way that it knows is its objective function is correcting it. That's the only way that it knows that it's right or wrong. So can it think for itself and say, well, maybe I shouldn't tell them this? I don't think so. I don't know if we'll get there. I haven't seen much work towards that. There's always some research in that area. Just people. There are. Sure. I agree with that, and I think it's a conversation that should be had. If you look at it through the lens of, I know what I know, but I don't know what I don't know. And the same thing can be said for these models. They know what they know what they know really well, but they can't extend out. They couldn't go learn a new thing. Does that make sense? but it's still a training process, right? So it's not like self-evolving. And I think to the extent of having something that's conscious, it has to be able to self-evolve, right? It has to be able to, it's kind of like Skynet, right? So Skynet is like, okay, it's a human creation, but I don't like humans anymore. I'm just going to, make these Terminators, and we'll be done with it. So, but I think to get there, you have to get past the idea of training. So there's got to be some breakthroughs where you don't have to have labeled data, you don't have to train, for us to get to that level of something that could be considered like a conscious entity. That's just my opinion. I know some people argue that hey, we're already there with the generative stuff. I just don't think we are yet.
So towards the beginning, you mentioned that nothing has passed the Turing test yet, partly because ChatGPT will say, hey, I am not a human. And I think that's a good guardrail to have, good and ethical. But does that mean you can have an ethical AI capable of passing the Turing test? And if not, is there another test that people have come up with?
In terms of ethical, I'm probably the wrong person to ask. I focus more on like the modeling side and the math behind it. The guardrails, I think those guardrails are there for a good reason. You don't want to ask ChatGPT like, hey, it's kind of like going to WebMD. Why is my elbow turning blue? Oh, you're dying. That's what you get. So I think it's good to have that. Guardrail there. You could take it off, and yes, you could argue that it's passing the Turing test, but you could stump it. You can get it to hallucinate. Just as an example it's telling you what it thinks you want to hear. I was writing a proposal, and me and several of my colleagues, I said, what if we just told ChatGPT to do this? And I told it, write a proposal in the style of Dr. Jeremy Davis, et cetera, prompt engineering stuff. It spit back this really nice sounding proposal, but you start digging into it, all those references were fake. They were from fake journals, fake conferences, stuff I'd never done. It was telling me that I'd worked on missile defense, and I've never worked on missile defense, just stuff like that. So, it starts hallucinating, trying to give you what it thinks you want to hear, but it can't. So you have to correct it, and I think that form of correcting it is where you get into the point of we're not there yet with it, truly being able to fool you. Like, it's the closest that we have, no doubt. Like, it's crazy. It's a great tool. I mean, it really is. It speeds up everybody's productivity, vastly. There's some things I just wouldn't trust it for. Not that I know of. I haven't really looked into it very much. The Turing test always comes up. It's one of the first things you learn in your intro to AI class about, Turing and the test and all this different stuff that he did, all these fields that he created. I hadn't really looked at the test anymore. When I was doing some research to put this presentation together, I was like, that's interesting, because they were talking about, there was a big debate about ChatGPT passing the Turing test. I thought that was pretty interesting. Well, see, Turing also started cryptography as a discipline too. I don't know if I mentioned that before. Oh, okay. So, yeah, and honestly, I watched these movies. I loved them. I knew I wanted to work in AI. It's just such a fascinating field. It's one of the more rapidly evolving fields now. It wasn't really up until the mid 2010s, just because of deep learning and all these. Really, the programming languages have made it easier to experiment with. But I digress there. So I kind of put it on the back burner. I got out of high school. I went to work for a couple of years. I went to sign up for college. I'm hot-natured. I'm burning up right now. I went to Mississippi State. I get there. I was going to be an electrical engineer. That line was really long. I was hot. We were outside for whatever reason in the middle of the summer. That line was long. There was nobody in the computer science line. I like computers, so I went to sign up for computer science so I could go get back in the air conditioner in my car. It worked out pretty well, I think, at the end of the day. So. Thank y'all. I appreciate y'all.